When you query a large database, the system faces a specific physical challenge, locating one exact data point hidden among millions of others. The basic approach is linear search. An indicator checks every single item in an unsorted array, one by one, moving left to right. Zooming out to millions of records, this fails. The indicator makes zero perceivable progress. Every incorrect answer is tested first. Because a linear search requires up to n operations for n elements, the latency grows at the exact same rate as the database. The system slows down as it becomes more useful. To bypass that latency, we need structure. The absolute prerequisite for binary search is that the data structure must be completely sorted beforehand. We slice a sorted array down the middle. The center element reveals if our target is higher or lower. If lower, the right half shatters and disappears. We center the remaining half and slice it again, iterating this halving process until one block remains. By organizing the data up front, sorting transforms the problem from a sequential hunt into a rapid process of mathematical elimination. Translating this halving mechanism into code requires us to track boundaries. This diagram shows a clean array of numbers framed by two pointers, a blue L pointer at index 0 and a pink R pointer at the final index. These frame our active search window. To physically target the center of these two boundaries, the algorithm calculates a yellow mid-pointer that drops exactly halfway between L and R. Next, we apply conditional logic. If the target is larger than the mid-value, the L pointer physically jumps past the mid-pointer to a new position on the right, instantly shrinking the highlighted active search window. If the target were smaller, the R pointer would shift left. These dynamically shifting pointers trap the target value in an ever-shrinking vise. The system isolates the data logically, avoiding the expensive process of deleting or altering the actual array in memory. Implementing this in C++ contains a notorious trap. This diagram shows the standard midpoint formula, where mid equals L plus R divided by 2. If you test a massive array, L and R spike to extremely large integer values. Their sum exceeds the 32-bit limit, turning the equation red and triggering an integer overflow error. We avoid this using a safe implementation. Mid equals L plus the difference of R and L divided by 2. By subtracting first, we prevent the variables from exceeding memory limits, keeping the integer capacity gauge safely in the green zone. The second trap is the off by 1 error. Notice this C++ snippet highlighting L equals mid plus 1 to bypass the checked midpoint. If you shift your boundary to exactly mid instead of mid plus 1 or mid minus 1, your search window never closes, and you trigger an infinite loop. Memorizing the halving concept is easy. Understanding the specific edge cases of hardware memory and boundary logic is what separates professional software engineers from hobbyists. This line chart compares two trajectories, a steep, rapidly climbing red line labeled O of n, and a low, flattened green curve labeled O of log n. This represents logarithmic time, the formal mathematical term for an algorithm that divides the problem size by a constant fraction at each step. To see what this curve means in practice, watch as the data points populate. Searching an array where n equals 1 million maps precisely to a maximum of 20 steps on the flat logarithmic curve. Compare that to the exact same dataset under a linear approach, which requires a full 1 million steps. If we scale the horizontal axis up to 1 billion, the linear O of n line shoots wildly off screen. Meanwhile, the O of log n curve barely rises to 30 steps. Searching a billion records in just 30 operations makes an O of log n scaling profile resilient to dataset growth. This logarithmic efficiency explains why modern search engines can query global indices without slowing down as the internet expands. To execute this correctly, 3 rules are non-negotiable. The data must be sorted in advance, the boundary pointers must shift past the checked midpoint, and the formula must subtract before adding to stay memory safe. Switching from linear to logarithmic search turns a seconds-long delay into a millisecond operation, keeping systems responsive as datasets expand to a massive scale. Mastering these pointer mechanics provides the specific logic needed to implement more complex data structures and high-performance search engines.